Hello. We remember by previous video what we've discussed. That's the introduction to tangents as such in the coordinate geometry. Those who are joining first, I think you know what to do. This link down here, can you peruse the previous video first so that we have to see what is there and be with us. Right, so here we are just simply continuing what we did in the previous video. Now we are solely going to work out on the problems about the what? Gradient. Right, by what we discussed previously, here now we have no time to talk of the whole story, but rather we just have to bridge the two, previous video and the present one. That what we have is just about the gradient. So what we introduced earlier was just like what a gradient is and how to calculate it. So I've just talked on that only. But then we go into the practices. So briefly, gradient, we said, is simply the measure of the slope. And we said this measure has something to do what happens along the x-axis and along the y-axis. So what happened there is just like a change on the y-coordinates and the x-coordinates. As such, if we were to come up with the formula of which we'll talk of the changing, this is delta y to delta x. Talk of the change in x to change in y. So what you get out of that, that is what is known as the gradient. And also observe that the gradient of a particular line is just exactly the same as the tangent of a particular angle, an acute angle of our interest. Right, now we talk of an acute angle in the right angle triangle. Find the gradient of the line, be able to see that that one is in relation to that. Right now, what we do now is simply to work out some problems using that formula and hope to see how that one works. Let's get into examples. Right, we have this question here. I'll just give you only one problem, that's enough. Find the gradient of a line segment passing through the point C that is 4, 3 and -2, -3. One connected topic and very logical. Define the gradient. We have known how to find the gradient. Relationship between gradient and the tangent, or relationship between the gradient and the what? Tangent of an angle. And here we now have good problems. So here now we are, without wasting our time. If you are given such questions, just know for sure that what it is there is just about a line segment. Here you have got 2 points, this one and that. So if you are there to have a Cartesian plane, you will be able to search for the position which is defined by 4, 3. And another position defined by -2, -3. So here maybe just to draw a sketch of yours in the Cartesian plane, if you are there, you can talk of the 2 points here. On the positive part, we have got here, x is 4, y is 3. These are the negative part on the other side of the negative side of the x-axis and y-axis. So there you have got the x -2 and y is -3. What is the measure of the slope? So here we're talking of in relation to the, that's what, horizontal axis. So without wasting time, what we do there, we just indicate the formula that say gradient is into y2 minus y1 over x2 minus x1. That's all. So the issue here, you don't have to memorize. That's it. Which one should be my y2? Which one should be my x2, and which one should be my y1, and which one is my x1. That is another crucial part, because some people just be taking, let this one be y1, this one be y2, because they're both y's. Right, so one thing here has to be known this way. What determines to be something as a 2 is something that sometimes you choose yourself. You can regard it as maybe by movements from wherever ends you are starting from and where you are going. So if maybe this is my slope, I decide to make this slope, it means I have to go along that line. It's either I can start from the edge here, I'll be going up like that. The moment I'll reach that end, it means I'm going to fill that slope. So if my movement is upward like that, it means where I'll end, I'm going up. All these ones, both these ones are 2's. So which means this one it'd be y2, this one is x1, x2. That's the way it goes. If you don't want that, then it should be the opposite way. Fine, I'm on the top here. I need maybe feel like going down, if you consider that one as a slope. So what do? It means you'll be going downwards like this. So it means as you go down like that, you're going to feel that slope. So it means the end point is here. So where you finish it means these ones are your 2's. Those ones will be what? Will be 1's. So it means this one, it'll be y2, this is x2. So it means any one of those points can be 2's. The other ones can be 1's. So the choice is yours. But don't do it this way, that say if this is y2, and you regard this one as y1, and you come here and say this one is x2, this one is x1. So how do you describe the change in that case? It doesn't make sense at all. Right, so the thing should be, one point should be 2's, the other one is 1's. Both in that pair of ordered values, that are 2's, then these are 1's. If these to you are 2's, then these ones are 1's. So I have emphasized on that one. Otherwise, the problem is simple. But instructions are very, 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 very important to understand. So take me that way. So in my case, I will regard these ones as 2's, these ones are 1's. Hence, my y2 here, it should be 3. And y1 there, it should be -3. So here, -3. X2 here, it should be a 4. And then x1 here, it should be -2. Look at that. Hope my explanation is clear, more especially when you're deciding which coordinates should be defined as 2's, which one as 1's. Don't make mistakes. So what we have here will be a value that is a ratio defined like 3 minus -3, that gives us a 6, and 4 minus -2, that one gives us what? 6 again. So it's just like 6 to 6. That's what we have there. So if you talk of the gradient in this case, it's just like 1. You are free to divide this one into that one, and that ratio can be divided by a single value. So here you can say 6 into 6 is what? Is equal to 1. You can use that single value to describe the gradient. So the gradient here is 1. Right. So please, that's the way it goes. Hopefully, you can do the same. For all lines that you can draw in the Cartesian plane, work the gradient like that. So I feel like with one example, everything is clear about this. Out of gradient, can we now go to the other section? This is issue that has now something to do with the distance between 2 points. Remember, we are going to study the line in depth. First thing you draw the line, what you know is line must have a gradient. So do I know how to work out the gradient? Do you know the meaning of a gradient? Issues of gradient are done. Now we go to what? Distance. The points you connect, they form a distance. So here we go. Distance between 2 points. I'll have examples of the points on this Cartesian plane. Allow me to change the axis and the scale as such. You can choose any line to present the rest of the top of the axis. Instead of having this one on the mid now, I'll choose this one. This is my y-axis. And then I've chosen this one as my x-axis. Height, look at that. The point where the two lines intersect, that is point of origin. And we have got the value of x as 0, value of y as 0. So I'll go by my own scale and you can decide your own scale. Possibly if you have a graph paper, I think you can do as I'm doing here. So let me use the same scale, say 2 centimeters representing 1 unit. So I'll jump 2 boxes here, considering all boxes are square boxes, right? 1 unit length. So I will regard this one as 1, this one as 2, that part as 3, this one as 4, this part as 5. So here it will be -1 and it goes on. Then here 1, then here 2, here 3, here 4, here 5. Down here is -1 and here is -2. Right, here we are. And that's our good presentation of the Cartesian plane. Right. Now from here, suppose I choose any points and you're going to choose yours. What I'm doing here is not something that it goes by that. It's just like a representation of all other activities you can do about the points. So you can choose any position. Like in my case, I may decide to choose a point. So in short, try to choose point of the Cartesian plane, any 2 points. In my case, I'll choose this point here. Let me choose this one. That point is described as point M. That is found at x is 1, y is 2. Another point I'm going to choose here is point, the point at this position. At what position should I choose the other point? Let me come here. Right. This position, MK. While K is found at x is 5, y is 4. Right. 2 points. The type here, distance between 2 points. So I've got point M and point K. Remember, every point has to be described by the what? 2 values. We call them as coordinates, x and y coordinates. That's about coordinate geometry on the Cartesian plane in relation to the straight line. So now, if I'm to find the distance between 2 points here, I have to consider several issues. It's more like you are more like working out the length of a line that is going to be connected between M and K. So the distance between M and K will there going to be represented by a line. So what I'll do here, I'll decide to draw this line here like this, connecting M and K. So in your mind, always you have to consider that if we talk of distance between any 2 points, that distance can be represented by a particular line. So now here, if I'm to discuss with you on how we can work out the distance between 2 points, what I'll do here, I'll use a line segment K, M. Right, so if we can try to analyze things here on the Cartesian plane together, you'll be able to realize that if we are trying now to consider the best way on how we can come up the distance between M and K in to be represented by line MK, you'll be able to see that what we need to do is just like a matter of finding the length of MK. Simple that. Now it'll be like, now how can we find the value of MK to represent the distance between K and M? So as it is on the body, you can at least drive up some mechanism to say, as far as I see that, issue here is about just MK. Considering what you have learned in the past, maybe you have good ideas. You find that if you think deep, you'll be able to realize that whatever is there about the length of its, with a length, for example, just a length, to find the length of something, has to do with trig 1 and also talk of Pythagoras Theorem. So if I'm to think along those areas, I'd feel like Pythagoras here can do. But how Pythagoras can be done here is not all that direct. Right. So it's just like now, if I'm to insist using Pythagoras, in my case, have to think about right angle triangle, because that's the only art. Without right angle triangle, it cannot work. So everything I think about Pythagoras, though I need to find the value of Km, I have to go by that. So now, it's that. So if you are to develop a right angle triangle here, you can at least think as a student to be able to notice that this Cartesian plane is a fill-up of the lines which are crossing each other, intersecting each other horizontal and vertically. And the way they intersect in such that they intersect at right angle. So you can capitalize on that and formulate what? A right angle triangle with the line itself. So like for example, that right angle triangle can come in this way. My line that of interest here is M, K. So now I may use M and K to come up with the addition two sides. So that with the existing line MK, they have to form a triangle. So like here with a K, I may think of extending K downwards like this by producing a line from K going downwards like that to anywhere point. And a line, another line can start from M going this way to anywhere point and have to see that this line from M has to intersect the line from K. So what will happen here is just like as line start from M heading towards this side here, you find that the line that is going towards this towards that direction from M, it will go like this. You see? And there's that line from K and line from M are intersecting at this point. We are within the lines which are vertical and horizontal, intersecting a right angle. Then first we'll have to consider that this line, this angle here, is right angle, it's 90 degrees. Because already wherever these boxes are crossing, so these lines are crossing, it's 90, 90, 90. So as such, I may not be able to consider this other part of the line and this other part of the line. It means the line should just end at this position here and have this point represented by maybe point D or whatsoever, like that. So that's the way you can formulate a right angle triangle when you're given any line segment on the Cartesian plane. So you can draw several lines with those points, let them go towards one side, and where they cross, be able to cross at right angles like that. So my target is MK, right, in the right angle triangle. So you know by Pythagoras, if we are there to use Pythagoras to find the value of MK, definitely we have to know the value of KD and the value of what? MD. Without that, let us not talk about Pythagoras. Right. So now, let us now fight and find the value of M, that is to D. What are the units? Here we just count the units because everything here is not measured in centimeters whatsoever. Right. So if we are to determine the distance from M to D, is just as good as talking of the change from M to D. And the number of units here, by what you have from M to D, you can go down there on the x-axis to say here I am at 1. It's more here just like at 1. The next, this is 1.5, then D is talk of 2. So it means that a gap from here up to that is 1 unit, like here from here up to that the same. So talk of what? 1, 2, 3, then 4. So it means from here up to that we have got 4 units to represent the length of MD. But not from here up to that is as good as when I'm here, it's just like maybe I'm here. When I'm here, it's just like when I'm here on the y-axis. So from here up to that is as good as how many units are here from here up to that. So it'd be like 1, then 2. So it means you have got what? 2 units as such. So it means the 2, 4 units on the vertical and horizontal axis respectively, they are going to give us the length of these two sides of the right angle triangle that will help us to work up the side of our interest. So let me capture that one separately like this. So this is our triangle that we have in there. Right, so this is M, this is K, this is D, right angle. Here, this is 2, this is 5. Target, finding MK. Right, so to find MK by Pythagoras Theorem, you'll be able to realize that say the distance that will go say MK, that one is just like hypotenuse side. So if you remember about the statement of Pythagoras, you talk of the square of hypotenuse side, which is MK. In this case, that is the target squared is equal to that MD squared plus KD squared. It goes like that. So what is MD? 2 units. So we write here 2 units, which will be 2 squared. Plus, what is KD? 2. So 2 squared. This one, MD is 5 squared. So I think here the story is just historical. We just do as we've been doing. 25 plus what? A 4. So what you get here is the square is just like what? 29. So all along here we talk of mk squared. Right. Just now, by Pythagoras theorem, we are able to calculate the distance between m and k. More like just calculating the side of a right angle triangle, length of that line. So if you are to find the value of mk, that's just like taking the square root of what? 29. And the answer that you can get from there, you can finalize that one out. You'll be able to get that is say, you'll be finding it is just like 5 point something there. And that should be in units. So this is one way on how you can come up with the distance between 2 points. Right. So that's by Pythagoras. So capitalizing on this, I may just be speeding up in order to at least help you come up with a formula from the same. Right. So the formula of which, in this case, I think we need to discuss it in the other video where I'll give you the example. Right. Because in this case, this is the only way how one can come up with the issues about the distance between 2 points. So you can use Pythagoras theorem to work out the distance between 2 points, formulate a triangle of that kind of size, more especially when you are given the what? Cartesian plane or a line segment already drawn in the line segment drawn in the Cartesian plane as such.